the Frank Hanford Miller Fellowship Committee. Committee consists of myself, Alethea Ray, and Nicola Armstrong. The Western Australian branch is pleased to host virtually this evening's Western Australia time speaker, Dr. Manuel Herrera, Research Associate, Institute of Manufacturing, Department of Engineering, University of Cambridge. This talk is fitting to be part of the Frank Hanford Miller Fellowship for more reasons than one. Frank was a member of the Western Australian branch of the Statistical Society of Australia community in his retirement, and also a member of the Royal Statistical Society community during his working life and beyond. He championed applied statistics and its relationship to the fabric of society, and indeed the politics of the day. Today's lecture is on engineering statistics and links the current generation of data and problems associated with it to telecommunication systems, maintenance of transport systems, resilience assessment of water networks, and optimal management of small ports. These all affect how we live today. The solutions and challenges in applied statistics are welcome. Without further ado, I invite Manuel to deliver his lecture, Research in Engineering Statistics, Current Trends and Future Challenges. Thank you, Manuel.
Thank you, Brenton. And thank you all of the Frank Hanford Miller Fellowship Committee, because it's to me a big honor to be here today explaining my work as a statistician, and as a statistician applying statistics in engineering for many years. It's to me a great pleasure just to talk with other statistician fellows, just not with the engineers. And now in my presentation, we are going to show you actually which is what that means actually to be a statistician and to work with the statistics in the engineering world for engineering problems. So let me share with you this presentation of these slides. Sorry, this. So actually, my presentation is about part of my work I did so far, and the work I'm involved in right now. And this is mostly about just statistics, statistical learning methods, and time series as well, just to work with and to face engineering problems. But what are the engineering problems we are facing? In the past, I worked with the water supply systems, and as an engineering problem, water supply systems required this control of the leakage, because this can become a big problem from a society point of view, from an economical point of view, and from even affecting other infrastructures in the city. So first thing happens to me when they explaining how it works, the water supply system, I thought it was a network actually, a network of pipes and demand nodes and water tanks. Basically, the one way in which people used to work with control of leakage and water quality problems was about creating district metric areas. So kind of isolated areas, a partitioning of the network. But they didn't use any statistical tool for doing that. Now about 12 years ago or something, I started my PhD actually in this problem, and I just focused on clustering something as simple idea as clustering that solve the problem of the district metric areas. Then, of course, many other research came after, because it's not only the problem of clustering. The clustering could be just used to optimize the resilience of the water supply system, to better control, of course, the leakage, as I mentioned before, or for any other reasons. Also, for water supply, I work in time series, and I just could make some difference in predictive models for demand management of water supply system. So it's a good land to a good topic to work with, and it's a lot of challenges to be done yet in water supply, as we are going to see later on in this presentation. But then today I'm working in different projects. One of them is about smart ports, and it's about the maintenance and optimal operation of ports, of quay cranes in the port of Felixstowe here in the UK. And just to make some numbers, this about 31 quay cranes, 82 yard cranes in this port, and a container. The point of this, the problem is that these cranes need to load containers. Each of them can weigh up to 35 tons approximately, and each of the boats coming can just carry out about 20,000 containers. So all these cranes in the port, need to work almost 24/7, and then any disruption on them may cause a lot of delays, a lot of disruption, and a lot of economical costs as well. So about an optimal predictive maintenance and a condition-based maintenance of the cranes is needed, actually. So now we are working in this in placing 5G sensors in the cranes, not in all of them, but in most of the cranes, and we are trying to ascertain when the failure may happen by predictive models, and also time series data mining as a tool to work with the data coming from sensors. Another different project is I'm working today is on the telecom networks. We are working in a maintenance and operation of the infrastructure of the telecom networks, also in the automation of the control and operation of it. And this problem is I'm focusing, or a way to focus this problem is on the anomaly detection. But the anomaly detection normally is just done in a time series as well. But in this case, we are going to have one different time series for each of the router stations, or that made the big network of a backbone network of an internet service provider here in the UK as well. So the problem of the time series and anomaly detection is scaled to a problem of time series just over networks. And we are working this problem. We are working in some distributed learning manners to approach this problem, in which each of the time series is not only informed by itself and the historical data coming, but also is informed by the neighbor of in the network, and how they are behaving. So this way we can just detect the anomalies in a better way, in a more accurate way. So there's a lot of challenges just related to engineering and applied statistics, and many other challenges will come. But most of them also, in general terms, they are related to some emergence of disruptive technologies that we are just witness today. So basically, most of the companies and utilities and infrastructure managers, they are just working to a digital transformation of the companies. And then for a statistician, it's necessary to understand what is this journey and what are the technologies associated to this, just to better get the results we want and better get the impact we want, not only from the academic point of view, but also from the applied point of view, and how this can be actually made a difference in the application of all data analysis. So many of the companies are just in the process of the digitization of the problems, that just changing these big files, handwritten files, to just using just computers, right? But now also most of them, they are in a digitalization process in which this analysis of the data already digitized is tried to be automated. But finally, what our company is expecting for is a proper digital transformation. That this is more about philosophical concept of how we work with all this data, or how can we use this data for the best performance of the decision making in the company. So at some point, this is pushing us to from the point of view of data analysis, to don't only just make the data analysis, but also to understand in deep the problem we are working with. And to me, this is one of the keys that we need to address as statisticians, because the data analysis by themselves are good, but they are not enough to give the answer to the requirements of any engineering project today. So in the process of digitization and digitalization, we just have a number of tools and technologies that are coming up today. And one of them is the IoT, and of course now supported by the 5G. The 5G, we just see how can just be completely connected. All the devices are connected in many fields in industry and engineering, right? So this gives us the possibility to actually work with the IoT, the Internet of Things, for better management of the systems, and better management of the systems in engineering. So what this is about is that we can have the information at in near real time of many devices that are encompassing an infrastructure. This opens the possibility to work better with data, but also create a challenge in the big data we are having so far. And I just see that in big data today, some people are just working actually in how to reduce this data without losing critical information. So here is another statistical problem that we need to face, is about how can efficiently manage the data coming from the IoT to these days. A way in which the IoT can be just managed actually is with the SCADA system, and then the SCADA system allows us to control the data and to control any infrastructure system. The way in which a SCADA system is working, SCADA is not new, it's not that it's disrupting technology, but it's interesting to see how the way SCADA works, because we observe here that the way in which SCADA is working is in a hierarchical manner. So this interconnectivity between the different devices and the different things encompassing the infrastructure is not a completely resilient. It's quite vulnerable, because at some point all of the assets are pointing up to a centralized solution, to a central point. In this regard, this blockchain can make the difference, and then blockchains allow us just to work in a distributed manner of all the big databases we are working in engineering. The security that is providing us a database as blockchains to work with engineering problems today is that we don't need to know the whole complete system to reach optimal decisions for that. So this is again some kind of distributed solution in which many optimal actions, only being aware of the historical data of your data environment and the data environment of other nodes in the neighborhood in this database, in that case, are allowing us to reach an optimal solution globally. And finally, the last optimal of the last disruptive technology is about digital twins and what they mean for asset management in general. I was in time ago, I struggled to understand actually the concept of digital twin, because to me it was kind of a simulation. And then this is why I want to try to explain, not actually for you, even for myself, to repeat it, that the digital twin is a more than a simulation model. We all are just used to work with simulation models, but the point of the digital twin is that this is such a simulation model, but fit by the real time data coming from the real infrastructure. And then with this data, that the response of the digital twin may change. So it's just this response of the digital twin is going to generate more simulations, of course, of the system, but the simulations are at a high level of accuracy of the model, they are representing the model in a very accurate way. So the digital twin basically is just going to mirror the real asset, and as it is informed by data collected in the real asset as well, the simulations just happen on the digital twin. They are going to be very accurate about what could happen in the real life. With the digital twin, therefore, we're going to have very accurate simulations of different scenarios that we can be interested to force in the model, and to see how the infrastructure may have a response. So it is very useful for asset management and predictive maintenance, for instance, because we can work in this sort of what-if scenarios that allow us just to take a better informed decision making for all asset management. But after presenting a number of technologies, have a thought about that is not about the technology we are using, is about to extract the maximum information from the technology we already have for a better infrastructure operation and management. So we don't need to push if we don't have the possibilities of having this or that technology. What we need to work always is just to get the better performance of the technology we have available. And this thought came because in some cases, people with not many resources in small companies or other countries that are not as with lots of resources, they're asking me that how can this be useful for them? But I always think that the usefulness is about how the data analysis about the data you have help you out in your business and can help you out in the industry. So what are, after having this range of methodologies, then we also need some, after having this range of technologies, we also need to have models and methods that are just companion of these disruptive technologies. And first, we need to just probably change the traditional thinking of cause effect to a more complex thinking of the problem, because we observe now that any infrastructure or any system is not just a collection of different independent devices or different independent assets. They are communicate between themselves, and actually any failure in one single part of the system may propagate and may affect to others. So we need just to think about this interrelationship of the problems and decompose the problem in several parts and analyze the parts, but also just synthesize the problem in a better analysis and synthesis of the challenges we are facing. And for better model these relationships, to analyze also the relationship apart from the analysis of the different assets, the networks are just coming into the picture, and then there are going to be communication networks in which just the sensors and different parts of the cyber physical systems are interconnected. So this is the part of the IoT, but also in many cases, we are going to work with the real networks composed by real nodes and links. This is the case of the telecommunication, the water networks, the road network, and transport network. And then all of them have been traditionally modeled as networks, but we didn't explore part of this network dynamics as much as we could. So I think this could be another option just to work towards, is about the network dynamics and how the traffic in the network can be modeled, and how the models in this vary from one type of infrastructure to another. So in many cases, we are working with this diffusion process over a network, right? But this is sometimes it's not enough when we are facing real problems, because this should be adapted to the network to the dynamics of the traffic flow in a specific question. Other challenges on modeling infrastructures and engineering problems as networks are coming from the heterogeneity of the assets or the parts composing the network. So these last years, multi-layer networks came as a very innovative methodology to work with these networks. So we can just work with network of networks in a separate way, but also just trying to model how these different heterogeneous different networks can be related between themselves. This is important for a single infrastructure, because in a single infrastructure we have a heterogeneity of different single assets, but it's also important for working with the interrelationship between multiple infrastructures. For instance, how the electric power network may affect the transport network. So some disruption in the electricity power can just disrupt the metro service. And of course, let me talk again a bit about the network dynamics, because this is another challenge to face, and we are working with now in this. And this is about how just to merge these two worlds of networks and time series. One of the possibilities of merging this part is just with a via network representation. So we are going to work a little bit more about this later on, but basically it's just how can we represent the network back to that kind of Euclidean space, and then work with the time series on this new space in which the network has been projected. So this way we can just still using the traditional idea of time series over some new vectors and matrices that are representing the network. And of course, the predictive analytics are key as well for the engineering today and for the applied statistics. Again, in this part is all about time and how a system evolves over time, and how can we control the system by IoT devices, cyber physical devices to reach some predictive maintenance and decisions even in advance that any issue may happen to us. And this can bring us the ideas of optimization over the future that may happen. So it's not only just thinking about the optimal reliability of the system, but it's also just thinking about what could happen in advance, what are the risks, and what is going to be the future scenario, and what action can be taken now in just to prevent future disruptions or future problems in the infrastructure or in the problem we are just taking on. So predictive analytics is something like blending, in my view, is blending some time series and regression analysis tools to optimization of the problem once the problem is just projected into what would happen next. Also, predictive analytics can be understood as a part of the anomaly detection methodologies, in the sense that we can, again, if we detect some anomaly, we can still plug this part of the optimal decision making over the work and proposal. So it's a bit more something else than time series. I think that is something is just merging the optimization part of solving the problem solving. And just to finish all this this view of different methodologies, I should mention that there is another new trend of explainability in machine learning and artificial intelligence. So this is not new. People always have been interested on explaining the models, but today is start to be a must when we are working with companies and industry, and then they need an explanation about what we are doing and how we take this any decision that may be have associated a high cost for them or high investment first, but then we are going to be very accurate in the decision and can bring some benefits for the company, but they need to trust in the statistical in the machine learning and artificial intelligence models. So one way to work with this is just working with the more traditional now statistical learning models, and then just try to explain how or try to interpret that models, provide an interpretation of the parameters, and provide an interpretation of just why we are taking the decision and how the model is working. But of course, there is another part about the new trend also in machine learning is about deep learning, and in which there are completely black boxes that can be very difficult to interpret, but we need just to make this effort to open the black box at some point to try to give the companies and to give the industry explanation of the parameters and how the weights are just selected, and what could happen if we just train the network differently, or what would happen if we just take any intermediate decision, and how this affect to the final decision making in the company. So in all of this, I do believe that statistics will are playing an important role on, and then they are going to be essential for this explainable part of the data analysis that now there is quite a requirement for working with the many companies that want to be part of this, not part of the analysis, but part of the solution and they want to know why these decisions we just can't recommend, why are they taken. But summarizing this part of the different technologies, I would say that this, again, another personal note that is not about the methodology you are using, is about how to approach proper engineering challenges for a better infrastructure system operation and management. So again, let me insist about it's necessary to know well which is the engineering problem we are working with, and then try to solve it. Doesn't matter the tool, but need to solve the engineering problem. And then this is a way just to make more impact from in industry, and this is also the challenge for us as statisticians, because it's not only just working with data analysis and that's it. We need to work in a multidisciplinary aspect of the problems. We need to engage with people from companies. We need to engage with engineers. We need just to push ourselves to better know many other problems. So it's more like that than actually the data analysis itself, and just the solutions we are going to take in the practice are just need to be adapted, completely adapted to the problems we want to, or we need to face. But let me just put an example of analysis. Maybe it's a bit more fun. This is the long-haul internet backbone network of BT. BT is one of the biggest internet service providers here in the UK. And okay, now this looks like we see here red nodes that are super routers, main router stations in which the big internet is coming to the country. Then there are regional routers in orange color and metro routers in green. This network is very dense, is highly interconnected, and then just to and at the end of the day, most of the problems may happen in the metro routers or the metro router stations that are closer to provide the service. It's still not providing the service to the customer, but they are closer to this. And then the moment we are moving to the closer to the customer, is the more likely the possibility to have some problems. So I decompose this network in different network slices. One I call the extended outer core. So this is made by regional router stations and metro router stations. We see this on the left. On the right, we see the extended inner core network slice. This is made by the big super router stations and regional router stations. We see that this inner core is almost completely connected. Is a small wall, has a small wall topology, while the other, the extended outer core, is a kind of a ring topology and resemble to topologies of in which we can just take scale-free topologies in which we can just have that these isolated nodes at the end. They are not going to be isolated in real life. They are going to keep going to other nodes closer to the customer, but we observe that here may happen more, these nodes may be more vulnerable in the topology, or may be more likely to have some problems. To analyze I wanted to analyze the network traffic passing through this network, and I focus on these two different network slices and the analysis. And this is what I had, and then I create some graph Fourier transform of the signals over the network, and each graph Fourier transform can give us a vector of the spectrum of the graph Fourier transform every time we just collect, every time or a step over the time series. So if we just concatenate all the results of the spectrum of the time series, we can just have at the end of the day a sequence that can be understood as a time series. In this case, I work with the time series matrix profile that for the anomaly detection. Matrix profile, we just can go deep into this in the workshop we are having next week. The matrix profile is a methodology in which by intensive computing of distances in the very own time series, we can be able to detect the most repeated patterns in the time series, but also the patterns that can be understood as a discourse on the time series, and ultimately be candidates to be anomalies in them. So in this case, we just see in red market where the discourse are, and in time, if we just go in this way in time, we see that the discourse happen at night, half 12 in the night and past 10 past 12 in the night, often happen at that time, and then just talking back with the BT, with the internet service provider, we discovered that this discourse occurred because of the maintenance operations of the infrastructure. So at some point we didn't discover nothing that they didn't know about, but we just checked that this method actually worked well, just to detect discords and anomalies. And actually this is what all is about, is just to try to extend, not using only a few days, as this is the case of this example, not only using 1 day or 2 days of data, but trying to use many days of data, trying to get a lot of different discords, try to engage again with the company and classify these anomalies because this maintenance operation in practice, anomalies because there is a peak of use in the internet for some reason, or other anomalies we don't know. So we can basically, this is the first step to our classification or automatic classification of the anomalies that happens in the network. And this is good as well. Or the other benefit is that we can have as well which node is the node in which happened the anomaly. If we go to the time series, specifically time series of such a node, we observe what is the what looks like any anomaly in this case. And the anomaly is more like instability in the time series, more than peak or a trend. Is this kind of anomaly so far is looking at some increase in the variability, out of the sudden increase of the variability of the time series. And then we can just use this information to classify all the anomalies or the discords in the time series coming from maintenance operation in there. But then having also this analysis is key as well to reproduce them in simulation and to work with these what if scenarios we just mentioned before. So for instance, we just observe here how they can simulate this. This is not the real data. This is now simulated data based on the observations. And then we don't only have the discourse of the problems that will happen in the network. We can gain more information about how the links that the cables are used, and how is the use also of the routers. And then we also here in orange the disruption during the time that is happening in the original time series. So we can recreate at some point the many disruptions in a simulation environment, and it's going to be very useful because coming only from the information given by the network traffic over the nodes, we can also get the information having in the links. That is also very important because the cables of the network are going to be a key actor in these telecommunication networks. And we observe here how the queue of data packets at each router station is growing. So we just cut off the number of data packets with a threshold, but we observe how it's just behaving the pattern of the utilization of each of the nodes in the network. Also thanks to the simulation that is based on the original time series over the network nodes. So to wrap up, let's just keep thinking about what research directions could we take as statisticians. But it is an open discussion. This is not only it's not a statement I want to make. It's an open discussion just for all of us, just thinking about what could be next and what can be actually the new paradigms in engineering that we need to meet as in the data analysis to work with, and how can also just get the best use of this emergence of disruptive technologies. Yes, we talk about the need of the explainability and the need of the having models that we can interpret, but we just didn't mention, but it's also very important. We need to add as statisticians certain capacity of generalization and modeling the ascertaining of the problems. These paradigms are not very. The machine learning and deep learning models, they struggle with generalization and modeling the ascertaining today. So we need just also think about this as probably a new research direction. And in the personal work, I should say that, okay, I will keep working with statistical network analysis that in my view still is a lot of work to do there, but also with the time series in networks that would happen in the data traffic as we saw before, but also time series on networks that because the networks can evolve not only in the data coming inside the networks, but also the networks may evolve themselves with links appearing, disappearing, links and nodes of the network depending on the availability. Also from the point of view of time series data mining, the anomaly detection is a must for the future, and also the challenge is just to work with very long time series. It's a real challenge to work with the big data, and now I'm just suffering this, just trying to work with a huge database coming from the SmartPort project we just earlier in this presentation. But just speaking of this time series in applied engineering, in interrupted time series, and are now very important, mostly because they become a new trend because the COVID, right? Everything changed, and not only changed from the biomedical point of view, but also from an engineering point of view. The energy use, the internet use, all the use of the utilities, they just shifted, and then there was interrupted, and the transport use in a city as well. So how can we model this from the time series? Is there's the interrupted time series. It's nothing actually new, but I think that the application today of this in the new environment we are on, a new real life we are living today is important. And finally, something that is just taking my attention these days is the IoT time series, in the sense of, okay, there are time series in the stream, but also they are taking at irregular time intervals. So this is a challenge as well, just to work with this kind of time series that, and then I think we need, or I will need to work with them in the future. And basically, that's it. Thank you very much for attending this talk. And this is time for any questions you have. Thank you.
Thank you very much, Manuel. I'll ask you to thank Manuel.
Thank you.
Right, now, rather than have a sort of free-for-all, perhaps people can raise their hands either by the reactions. Seeing any hands? Well, I've got a question in to start with, or comment actually. As I have control, I can be selfish and get my question in. I have a sort of a high-level question, I guess. I think that the statistical methods provide one with enough tools. Of course, they're constantly developing as well, but leaving that aside, the statistical way of thinking gives one enough tools to address the sorts of problems you're talking about. But the thing where I think statisticians have often been lacking in is so the thing that statisticians I think have often done is seen problems as too small, and not looked at the large thing that I think you've called systems thinking. I think that has two sides to it. The people we're talking to, talking with, collaborating with, often don't have much of an idea of systems thinking either. I think the explainable models idea goes a long way to addressing that. I mean, my experience is that people won't use stuff they think they don't understand. They don't like using magic. But I've taught engineers statistics in a couple of universities, and my experiences are that the statistics they're getting taught is pretty basic as an undergraduate. And it's very frustrating to teach some of those things because they're boring for statisticians to teach. There's no excitement. It's, it's confidence intervals and t-tests and stuff like that. And that is such a far distance from what you're talking about that I wonder, if you have any thoughts about sort of engineering education in statistics, as well as sort of statistical engineering, statistical education. I'll try again. Statistical education for engineers and engineering systems education for statisticians.
Yeah, you are right. I think there is a big gap between these two worlds, and this was also the reason why I just thought about the topic of this talk, because there is a lot of not very high level statistics books for engineers, and engineers just make some very basic statistics, but they actually at the end they struggle when they just go out because they can't use the cutting edge methodologies they probably need to use, and they need to learn most of the time by themselves, or they need to just do another degree or something. Otherwise they can't just actually work with this. But there is also a risk in which they just using it and they don't know actually what they are using. And this part is also, this is another counterpart of all of this. They have a lot of tools available, and they start to play around, and they actually don't have the fundamentals to know exactly what they are using, and this is a problem. But also for us, for the part of the statisticians, also, yeah, we need also get more grasps of the ideas of what a system is and what engineering is and what all this represent. So still, I don't know, but I think that could be easier for us to know about engineering than for engineers to get this take a step forward to know about data analysis. I don't know, but still it is a work to do in both sides actually. Yeah.
Thank you. Melinda's iPhone has a question.
So I'm the engineering interloper on this call, so forgive me. And I agree with everything you've said. So we are woeful at statistics. Engineering education statistics is woeful, and professional engineers have woeful statistical capability in the main. There are exceptions, of course. My question for Manuel actually is one that bedevils me and my statistical collaborators, because I don't pretend in any way, shape or form to have much statistical background myself, is this issue of ground truth. So there's a huge, my area is predictive maintenance. There's a huge amount of work and pressure in predictive maintenance. There's lots of people selling snake oil solutions. But in my experience, we often have a huge uncertainty about what actually happened. So it's okay if a network went down, that's really clear. But if a piece of equipment fails, that's not always well documented. And there's a huge amount of uncertainty. You see covariates change, and then the thing is removed, but you have no idea whether it's failed or not. And I wonder if Manuel had experienced this, because it certainly affects the work that we do here at UWA, not having a definite ground truth for our models.
Yeah, this is a very interesting question, and I think this is an open question just to solve. It's not straightforward. But one of the things I'm thinking now to address this is just some working with some sensitivity analysis, causal analysis as well, as a idea to deal with this problem. Probably some Bayesian perspective of the problem can give us some possibility to understand actually the cause of the root cause of the problems for optimal decision making for the maintenance. You're on mute, I think. Sorry, you are on mute, Melinda.
Melinda, we missed your question.
Yeah.
You're on mute.
Yeah.
My question, I suppose, is more specifically not whether we know what the cause was, but whether we know whether the thing happened at all. For example, if my blood pressure goes up, I don't necessarily have a heart attack, but I might go to the doctor. So you know my blood pressure went up and I went to the doctor, but you don't know that I actually had some negative medical event. I'm trying to put it in a health term, but often what we see is the temperature of a piece of equipment goes up, and I know somebody might see that and they say, oh, we're going to change it out. But did they change it out? And was it failed if there was changed out? This is a huge issue. Sometimes we see a symptom and we respond to it, but we don't know if the symptom actually manifests itself in a failure, but we tag it as a failure for statistical analysis. And I think this causes a huge amount of problems for simplistic data analysis of the type that engineers usually do.
I agree with you in the sense that it's necessary just to know in depth the problem, to better use this prognosis analysis of the system, and just better classify the issue that may happen, and then just take this also in a predictive manner, just to take it in advance. But also it's very important as well just to explain why we are just taking the decision we are taking, because the many costs may be associated with the decision we are taking. In the case of course, of the just medical prognosis, is the health of the patients that is in just at the stake. But in the case of any decision making in an industry, is also may come associated with the costs in the terms of economical cost or environmental cost. So it's necessary just to give them to give the companies an explanation. And I think this is a proper question, but it's an open research question also from the point of view of data analysis, because this is one of the research directions we need just to go towards, is just to better prognosis and analysis of the problems we are facing. But of course, other option is just to say something more specific, perhaps, is this what if analysis, that is they are part of the explainability skill sets we talking about. And this may bring us some other ideas about what could happen if this, what could happen if this, another, and just project the problem at the different scenarios, and just to help us in the decision-making process. I think.
We have a question from Alok.
Yeah, thanks very much, Manuel, for your talk. I've got a slightly more concrete question, perhaps less philosophical. In one of your earlier slides at the start, you showed photographs of some cranes at the port. Are you able to describe, even just in broad terms, what that project was about, what the failure modes are, you know, for those cranes, what sort of sensors you have, and what kinds of tools and techniques you're using for predicting failures and also for predictive maintenance?
Yeah, sure. We are just monitoring the cranes at the different parts of it, and then we are monitoring the engine. We are monitoring the ropes, and we are monitoring other parts of the crane. And with all of them, we just getting, of course, just time series of in the sense from out of the sensors. We also have some PCL data that supposedly is the ground truth about what is happening in the crane. And then we are just trying to not only just using the data from the sensors, but also crossing this data with the PCL data we are having. And the PCL data is just the data in which they are just getting, we can't know when which is the action is taking the crane. It's just loading a container, is just moving, with is the velocity. So with all of them, as we have this knowledge of the PCL of each crane, we want to see if the sensors are replicating or can explain at some point all the movements and actions of the crane. And in this way, we can just make some data analysis on the sensors when something happened in the crane, and we can cross the information we are getting from the sensors to what actually is happening in the cranes. And about the methodologies, yes, you mentioned that I'm actually using this time series data mining methodologies. I'm using matrix profile, also SACS, the symbolic approximation. just to work with this as a solution to the problem. But I also recognize the problem is getting bigger and bigger the moment we're having more and more data. And then I'm thinking on other solutions just to reduce even more the dimensionality of the data we are having and losing.
So just a very quick question, just to end off, Manuel. So how often do failures occur, and are you also measuring any degradation that's taking place in the parts of the crane, the different parts, whether it's the beam or whether it's a cable, whether it's the drive or the motor?
Yeah, we are making also. We are considering the current the state of the assets in the crane. There is we didn't start yet, but supposedly they are coming with images of the crane as well, just to detect if there is some leakage of oil or something in the crane also, and also the state of the rope. So with the images and videos that we need also to analyze further. And the failures are, disruptions are coming often, but big failures are not coming very often, I should say. But yeah, this disruption that we need just some kind of the crane stop for 1 hour or something, this is coming it's coming quite often. So this is probably one of the most interesting parts with the data we're having today. Probably with a longer period of data, we're going to find out more big failures, right? But with these small disruptions, I think there is a lot of efficiency of the port operations that is losing in these small stops they need to take. So with the preventive maintenance and condition-based maintenance, I think we can just make the difference on this.
Okay, thank you very much.
Thank you.
Do you have any other questions? Okay, Ross has a question, but he needs to unmute himself so we can hear it. Okay, we can hear you now.
Manuel, my experience with large data sets is a technology called non-invasive load monitoring for households, where meters on the house record the electricity signal thousands of times a second, and then that's transmitted to a separate place where it's processed, and an idea of which appliances are on in the household can be got from that signal. That involves a lot of data transfers and a lot of storage. I've also been involved in a project which looked at the road network in Western Australia, where a series of trucks transit the road network every year, and they record the condition of the road every metre, and they have lasers underneath the truck. My major problem with both projects was simply getting access to the data. So the data is set up for engineers and to use the data for engineering purposes, whereas as analysts we have slightly simpler needs for the data. We don't need all the bits and pieces that the engineers need. We're actually looking more, of course, at the underlying patterns in the data. What's your experience in that regard in terms of getting access to engineering databases?
My experience is that it's a problem for me as well. Actually, there is another colleague here that he's actually the one he's dealing with as a link between what is coming from the sensors and what I'm reading, and even that is a complicated thing to read. Even if just reading and storage, not only storage but reading the data is complicated. And also, okay, in this link between the data coming from the sensors and the data I receive, there is a lot of complication, and there's one person dedicated only just to do this job, and he's not a statistician. He's an engineer just working on this task, because it's necessary just to someone just to translate to data language what is coming from the sensors. So this is a huge challenge as well. Another challenge is just, as you mentioned, many of the sensors, they are coming as batches of hundreds of thousands of data per minute. And then all of a sudden you say, okay, no, fair enough, I don't need such a quantity of data, and I'm just trying to transform the data before I receive the data, just with some Fourier transform or something, just to get only just some expression of this data, because to me the resolution of this nanosecond is meaningless, and I also think that for the operation of the maintenance of and the real-time or near real-time operation of decision making is too much. I mean, could just understand 1 second, but 1 nanosecond of resolution is high. But they made this because it's some kind of synchronized, some engineer reason. They are synchronized with the engine, and then in this way they can just reproduce or detect better any anomaly in the vibration of the engines, but it's complicated. And this is also just what I'm just mentioned before, this IoT time series, because they are coming with a specific problems we need to solve. Yeah.
I've got one more, if I can ask. The crane model. Crane is a physical object which obeys the laws of physics in the sense that there's a lot of understanding about how it works, and you put a load on the end of the beam and things like that. The digital twins presumably incorporate what you might call as physics knowledge. To what extent are you able to exploit that, or are you looking at these things that you're talking about as pure sort of streams of data that you're getting? I mean, do you use the physical properties of the things you're trying to maintain? How does that work in your work?
By the moment, we are just we are at the early stages in this project, and then we are just analyzing patterns in the data and anomalies, of course, and just checking if the sensors are able to reproduce the crane movements and the crane problems. But we just the other day, by the way, we started just to think about the digital twin of a crane. Now the challenge will be that with all the patterns we observe in data, we just kind of reproduce or generate time series, replicating the time series we observe in a regular basis, and also replicate failure mode of if any specific asset of the crane fails. So it's a lot of work to do, and we will need lots more of data. I'm really scared about just working with such a big quantity of data, but we will want to work towards this direction as well. But still need a lot of work, because we need just getting data from the sensors, and at the end, just the idea is basically replicate this time series synthetically over the sensors as well, and then get back to the real PCL data, but simulating PCL data, simulating movement. At the same time, if we just connect at a near real-time database in the cloud of the database, coming from with information from the sensors to the digital twin model, we can just replicate the movements at near real time in the digital twin. And the idea again is just to inject some anomalies, some problems, some disruptions, and see how the digital twin behaves, and also which maintenance option could be better in each of these scenarios.
Thank you. Melinda, I see you as a hand.
I have a cheeky question, actually, if I'm allowed. My cheeky question is, as statisticians, you have a great ability to work across many different sectors. You have a fantastic set of skills. We all want that, medical, genetics, you name it. How would Manuel persuade a young statistician that it's worthwhile working with engineers?
To work in, sorry?
How would you persuade a young statistician that it was worthwhile working with engineers?
Good question. I think working when you apply statistics, any application is wonderful anyway, because what I love of this is just to see my work actually that can be done, have an impact in the real life, and then we can just get something done. But working in engineering is also very rewarding, because you understand a system, a mechanical system or a digital system, and then you can handle it, you can control it, you can just get the best of it, the best production in an automatic manner as well. So it's very it's wonderful actually working in engineering for a statistician, and it's a challenge as well, because it's a lot of work to do and a lot of work to be done. But it's complicated just to convince a statistician to come to engineering and not going to biology, that is beautiful, or going to medicine, that is very useful. And so it's complicated. But I will just approach this from the point of view, perhaps, of these systems, from the point of view of the relationship between the different parts of an engineering system, because this, to me, this is also amazing, and how can modeling and understanding this more than each of the behavior of separate parts of our engineering system, how they are related. And I think there is a lot of challenges we need to face in the future on this relationship between the different parts of a system, because so far most of the time we understand the system not as a system but a collection of different devices. But if we just started to work in this, working in the modeling of this interrelationship, is something also beautiful, and is amazing, and it's a lot of work to do. And also in other topics, there is a lot of people very experts on it. So in engineering, we can make the difference easier, I think.
I think, thank you very much. I think I might call it a day, or an evening for us and an afternoon for you. Thank you very much, Manuel. I ask you to join me in thanking Manuel. Don't forget that Manuel is talking next week in the workshop, 2 days, Thursday and Friday afternoons. Sign up for the workshop on the SSA page. Thank you very much. I'll say goodbye to everybody. Thank you for coming.
Yep. Thank you.